Hey, it's Dr. J. I'm back, and today we're going to learn about the definite integral. So we've already suffered through quite a bit of grueling calculations of finding the area under the curve, which is what motivates the subject of the definite integral. And we're going to get back into that in just a second. But let's just start with a definition. Of the definite integral. So given a continuous function, on the interval AB, the integral from A to B of f of x dx is equal to the limit as n goes to infinity, or as n approaches infinity, of the Riemann sum from I equals 1 to n of f of xi star. That's the worst star ever. Let's try that again. That's supposed to be an asterisk times delta x. Now, I've done a bunch of these Riemann sums. I was actually writing them the other way. I was writing the delta x times the f of x, but in this notation, we reverse the order. Again, these are being multiplied, so the order doesn't matter. So this is called the definite integral. We've already had a lot of experience with indefinite integrals. The whole beginning of Chapter 4 was focused on indefinite integrals, and now we have the definitive or the definite integral from A to B. Now, the xi star is any what we call sample point in a subinterval of width delta x. So we have these delta x subintervals, which is essentially the width of each rectangle. And it turns out that we can pick any sample point to be our xi star. We typically just omit the star and just call it xi. But since this is the definition, I'll be true to the definition, and I will keep the star there for now. Okay. So what's the idea behind this? Well, we've already seen quite a few Riemann sums. So let's get deeper into the Riemann sums and think about the idea. We have a function on an interval from A to B. So this is our y equals f of x. That's our function. And these are the Riemann sums, or a Riemann sum, I guess, of n rectangles. So just think of n as a large number. Right? And large is obviously not a objective word. It's just whatever you think of as large. So, I mean, if 10 is large, it's probably not, but I usually think, more than 10. So 20, 50, 100, 1,000, a million, whatever you like, right? And so you have all these rectangles, right? N is the number of rectangles. Right? It's the number of rectangles. And we spent a lot of time in the last couple videos, a grueling amount of time, talking about whether we were going to pick the left endpoint or whether we were going to pick the right endpoint or whether we were going to pick the middle. It turns out that it doesn't matter. We can pick any point. So if you have a rectangle of width delta x, that's the width of one of these rectangles. Right? The width of that rectangle is delta x. You can pick any point. Xi star can be any point. And then that point will obviously produce the f of xi star, which is what I was referring to as the roof. And it tells you where to put the roof or the top of the rectangle. Sorry, that's a terrible rectangle, but that is awful. You get the idea, I hope. It's supposed to be a nice rectangle. And if you have a large number of rectangles, think about it for a minute. The rectangles are going to be so many rectangles that they're going to be very, very thin, right? So n is now approaching infinity, that it really doesn't matter which point we use to define the size of the rectangle. And so that's the idea behind it. To really see the mathematics in action, we're going to spend a little time talking more about the Riemann sums. And then we will use previous methods, from chapter 1, when we talked about limits as n goes to infinity, to take the limit, and then that will give us the final definition of the definitive or the definite integral. All right, so all of that introduction, the section continues. I'm just going to start over with my numbering. This will be example 1 of the definite integral. Let's take the easiest function you could think of. Maybe not the easiest, but a very simple function called the identity function. F of x is equal to x on the interval from 2 to 9. Using 20 rectangles. Calculate the sum, or the Riemann sum, I equals 1 to n of f of xi delta x. And again, I usually omit the star just because it doesn't really have to be there. Where xi is the right endpoint. So we'll call this the right endpoint method. I think I might have given it away in the last video. It is my favorite of the methods. So when I, discovered or was informed that you could pick any point you want, well, if I could pick any point I want, and I've sat through all the different choices, You could even pick a random point. You don't have to do left or right or middle. Everybody could pick their own points, and you'll all essentially get the same answer. I'm going to stick with the right endpoint method, and we'll see what we get. All right, so let's go ahead and find the Riemann sum, or the sum. So let's start off by finding delta x. That's always where you start. So it's going to be b minus a over n. So my n is 20, my b is 9, my a is 2. So 9 minus 2 over 20. And that is my delta x, 7/20. So that's the width of each rectangle. It's pretty skinny, very skinny. Xi. Xi is a plus I delta x. Maybe I'll just put some little reminder formulas over here. Delta x is b minus a over n. Xi is a plus I delta x. All right, f of xi. Well, because the function is so simple, f of x is just equal to x, then f of xi is just equal to xi. You could also write this as 7i over 20. That's probably the way I would write it, just so I don't have to have all these extra parentheses. And then clearly n, I've already defined n to be 20 rectangles. All right, and now using the methods we learned last time, let's calculate the sum. The sum from I equals 1 to n of f of xi delta x. Again, the order of these doesn't matter. You can also write it this way. This is like saying the height times the width, and this is like saying the width times the height. When I first introduced the concept, I think of the delta x as going on the left, but it really doesn't matter. I actually prefer it this way. All right, so we're going to go from I equals 1 to 20. Our delta x is 7/20. And then our f of xi is, I'm going to get rid of the dot. I don't really need the dot. 2 plus 7i over 20. All right, so there's your Riemann sum. Now this is still finite, right? So I'm stopping at 20. So I'm going to add up 20 numbers. There are several ways to do this. All right, so there's your Riemann sum. It's a finite sum of 20 rectangles. There are several ways to do this. One way to do it would be to plug in 1, write down the result. That would be the area of the first rectangle. Then plug in 2, write down the result. And then make a big list, A1, A2, A3, A4, like I did before. And you would have 20 areas, 20 rectangles, and then you would just add up all 20 areas. And that would be one way to do it, all right? Another way to do it is to use one of the recipes that we had, right? And this one is pretty simple, because it only has an index of I. I have a choice about how I want to deal with the 7/20ths. I like to bring it out. That's one way. Sometimes I put it in to the parentheses, but in this example, I want to try it this way. That's a constant. It does not involve the index I, so it comes out. And then you're taking the sum of 2 plus the sum of 7I over 20. So you're basically breaking up the summand, that's what we call this, into 2 other sums, right? Now, if you bring the 7/20ths out, you got to be careful. It's going to multiply by the entire result of these summations here, which I've screwed this up before where I pulled it out and then forgot that I did that and then didn't apply it correctly. That's why there's another strategy, which is to not pull it out, but to just foil it in or distribute it in or fold it in. And then the 7/20ths would be in these summations and you wouldn't have to worry about forgetting it. All right, so this is the sum of a constant from 1 to 20, which literally translates into 2 plus 2 plus 2 plus 2 plus 2 plus 2, 20 times. So that's 2 times 20. Yeah. Or in other words, 40. 2 plus 2 plus 2 plus 2 plus 2, 20 times. Here we have 7 over 20. Oh, and by the way, got to have these brackets here because this 7 over 20 is different than this one. So this 7 over 20 only affects this second summand. And then I have the summation of I. So this is I plus 2. This is 1I plus 2 plus 3 plus 4. So I is equal to 1, and then I is equal to 2, and then I is equal to 3. So the I is getting larger and larger all the way up to 20. All right. Now, again, you can take out a piece of scratch paper and just go 1 plus 2 plus 3 plus 4 plus 5 plus 6 plus 7 and stop when you get to 20, right? Or you could use the formula 20 times 20 plus 1, which is 21, divided by 2. Yeah, this is the same thing as adding 1 plus 2 plus 3 plus 4 plus 5 all the way up to 20. So now you've got 7 over 20 times 40 plus, let's go ahead and simplify this a little bit. 20 will cancel. So I've got 7 times 21 divided by 2. And now I'll distribute this back in, which really makes me wonder whenever I do that, was it really worth it? Was it really worth it to take it out if I'm just going to have to put it back in later? I don't know. I'll leave that to you. So the sum from I equals 1 to 20 of f of xi delta x is equal to 7 times 40, so that's 280 over 20 plus 7 times 7, so that'll be 49 times 21 divided by 40. So again, I'm just distributing the 7 over 20 here. I probably could have canceled some things, but I didn't. I'll just do it now. 280 divided by 20 is 14. Yeah, I almost said 140, but 280 divided by 20 is 14. Plus, this one I'm just going to go ahead and do it. So it's 49 times 21 divided by 40 which is 25.725. And now I add these together. 39.725. I guess I've been rounding to the nearest hundredth, so I would probably do 39.73. That's rounded to the nearest hundredth. It's been so long since we started this process, I can't recall what the instructions were. Just a quick double check. Yep, rounded to the nearest hundredth. Yep. So this would be rounded to the nearest hundredth. That's the funniest looking sigma I think I've ever seen. My sigmas need some work. A good proper sigma looks like this. You know, that's a well-written sigma, but I get pretty sloppy with them as I go. Sometimes they end up looking like backwards threes or something. So that's a proper sigma. All right, so there you go. That is the area under the curve. It was a pretty basic curve, right? It was just a diagonal line, f of x equals x. So let's do another one. So let's try x squared. Yeah. From 4 to 6 using 50 rectangles. So f of x equals x squared is just the right, well, it's actually a full parabola, but I'm only going to look at it from 4 to 6. So I'm just looking at this little wedge here. I don't care about any of this. And I want to know the approximate area here using 50 rectangles. And I'm not going to draw 50 rectangles. Okay, so what's delta x? Delta x is 6 minus 4 over 50, which is 2 over 50, which is 1 over 25. As a decimal, look how small that is. 1 divided by 25, it's 0.04, 0.04. So very, very, very skinny rectangles. So skinny, I'm not even going to try to draw them. All right, there's your delta x. What's your xi? It'll be a, which is 4, plus I times delta x, 1/25. Or you can write it as 4 plus I over 25 if you want to get rid of the parentheses. There's your xi. And again, you can also call this xi star, but I think the star just makes it look messy, so I just call it xi. What else? F of xi. Well, now we have to do a little bit of math. F of xi is xi squared, which is equal to 16 plus 4i over 25 plus another 4i over 25 plus I squared over, I always forget what 25 times 25 is. And as soon as I do it, I go, oh yeah, it's 625. That's like an unresolved childhood issue of mine. I know it's 625, but I just go, on. I do it on the calculator every time, even though I know I'm right. I don't know what it is. I'm afraid to be wrong. All right, and then you can combine these guys, so you get 8i over 25 plus I squared over 625. So this is your f of xi, simplified. If you're lazy and you're just trying to get it done, you can leave it like this. Yeah, you can leave it like that, but you will eventually have to do this anyway. So it's just like putting it off for later. So, if you just want to get out the door, then you can certainly stop right there. But at some point, you're going to have to clean it up. So I just figured I'd clean it up now. All right. And then n is 20. Or no, not 20, sorry. N is 50. That's the number of rectangles. We had that at the very beginning. I don't always wait, but I did this time. So when I do my sum, it's the sum from 1 to 50 of f of xi. I like to put the delta x first. Delta x, and then the f of xi. So there's your Riemann sum. Now I do have to do the math. Let me show you another way. Whenever I have these really sort of annoying fractions, you can go like this. So I'll call this alt method. I'm going to wait on the calculator for now. I'm going to pull out the 1 over 25. Yeah, pull out the delta x out to the front. I'm just bringing my equal sign over to here. All right. And then I'm going to do the sum of 16. Just thinking of 16 as the constant. And then I'm going to bring out the 8 over 25. Now, I do got to be careful here. I'm going to put big brackets here. So this 1 over 25 is all the way out in front of the entire result. So I'm going to go 8 over 25, and then I'm going to do the sum of I. And then I'm going to bring out the 1 over 625, and then I'm going to do the sum of I squared. So this is the Riemann sum expanded, and then I have not calculated anything yet. And now watch what happens when you go to calculate it. I don't know if it's any easier, but so this is going to be whatever k is times the number of rectangles times 50. It's almost just like cleaning it up so that you can save the messy stuff for later. Then you have 8 over 25, and then use the formula for 50 rectangles. So that's 50 times 51 over 2. And then now I've got 625, 1 over 625, and then the formula for 50 rectangles, I squared. So that one was 50 times 51 times 2 times 50 plus 1. So that's 101. Right. That's that weird one that you really have to remember or have it written down. It's n plus 1, 2n plus 1, and then 6. divided by 6. So again, this one you can remember, 7 days a week. That one's pretty easy. You can teach this to a kid, yeah? Whatever the top number is, you just add 1 to it, multiply, and then divide by 2, right? This one's a little trickier. I mean, you can certainly teach it to a kid. They may or may not remember it. I always forget it. I have to have it written down. And I mean, unless I just did it 5 minutes ago, All right, let's do a little bit of cleanup here. We can clean a lot of stuff up. 25 goes into 50 twice. 2 goes into 8 4 times. Let's see. I don't know if this one's worth it. 25 goes into 50 twice. 25 goes into 625 25 times. 2 goes into 6 3 times. 3 goes into 51 17 times. I think that's it. That's as good as it gets. So I've got 1 over 25 times, and then now let's just bust out the calculator and do some math. So 16 times 50, that's going to be 800. This one I got rid of all the denominators, so I've got 4 times 2 times 51 times 2 times 51. That's going to be 408. This one I couldn't get rid of the denominator of 25, but I did do a pretty good job on the numerator. It's going to be 1 times 17 times 101. I'm going to erase that in a second. Let me just do it on my calculator. 17 times 1. I don't need the 1. So times 101 is 1717. That's cool. I should have known that. And again, if you don't want to do all this cleanup stuff, you just want to put it into your calculator, that's fine. I still get a kick out of cleaning up the mess before I do it. So let's go ahead and do it. 800 plus, let's do this first. 1717 divided by 25. That's 68.68. That's another cool number. Neat patterns we're getting here. Plus 408 is 476. 68 plus 800 is 1276.68, and then just divide by 25. Right. You can just pull this over here and divide the result by 25, and that gives you your answer, 51.0672. Let's see, round to the nearest hundredth. So the answer is the Riemann sum from I equals 1 to 50 of f of xi delta xi is equal to 51.07. So it's 0672. So I'm rounding to the nearest hundredth. Okay, well, that's really just sort of the warm-up for this lesson. We have not yet actually done the limit yet. So next, we take limits as n, the number of rectangles, approaches infinity. All right, so we don't want to settle for, 20 rectangles or 50 rectangles. Even 100 rectangles is not enough. We want infinitely many rectangles. So many that you don't even bother drawing them anymore. I mean, I've already kind of exhausted the ability to draw them. So evaluate the definite integral from -2 to 4 of 6x squared. Oh, sorry, no. Just 6x, not 6x squared. I apologize. I'm mixing up two problems in my notes, so start over again. Example 3. Evaluate the definite integral from 3 to 5. The -2 to 4 is coming soon. From 3 to 5 of 6x dx using the definition. I'll just say def. All right, so this is now the definite integral. So let's go ahead and write the definition. Right. The integral from 3 to 5 of 6x dx is equal to the limit as n approaches infinity of the sum from I equals 1 to n. So we're not going to say how many rectangles there are. We're just going to say that the number of rectangles is infinite, or it's approaching infinity. Of f of x, I, and again, technically it's got the star here, delta x. The star just looks so messy to me. I can never really draw it good. Maybe you can just do a dot. Or you could leave it off completely. All right. All right, so let's piece this all together here. Let's start with delta x. So what's delta x? Delta x is b. So this is b. This is a. Yeah, you got to read it from the bottom up. So it's from A to B. It's usually pretty obvious. A is the smaller of the two numbers. So it goes from bottom to top. So we're going to say B minus A, 5 minus 3 over n. So there's my delta x. Notice, because we have not committed a value to n is a variable, right? The answer includes the letter n. What are our xi stars, or xi blah? Or you could just say xi. We got to be careful. We're doing right hand. All right. I'm doing all of these with right hand. All right. Only because I prefer right hand endpoint. You're actually, I mean, unless you're, told to do otherwise, but, if you're doing this on your own, if you're, running your own show here, you could choose left, you could choose middle, or you could choose neither. You could go, I don't want to be like everybody else. I want to choose the third from the left, halfway between the middle and the right. You can even just go eeny, meeny, miny, mo and just randomly pick these xi stars. It doesn't matter, because the rectangles are getting so skinny, yeah, that the point that you pick in that tiny little rectangle is insignificant. The difference between the left and the right and the middle is it's so minutely small that it makes no difference. All right, so I always just go with right. All right, so it's A, so that's 3 plus I delta x. And I usually rewrite that. I just rewrite it xi. 3 plus 2I over n. Okay. And now f of xi. F of xi, well, this is our f. So that's just going to be 6xi, which is 6 times this thing. 3 plus 2i over n. And I distribute the 6. 18 plus 12i over n. So there's your fxi. All right, so now we have the integral from 3 to 5 of 6x dx is equal to the limit as n approaches infinity of the sum from I equals 1 to n of this thing, 18 plus 12i over n times this thing, delta x, 2 over n. You can use a dot. You can actually omit the dot. You could put an extra set of parentheses or not. I prefer actually to put the 2 over n in front, but it doesn't matter. As long as it's being multiplied, it does not matter what side of the parentheses it's being multiplied. It does matter that you have the parentheses initially until you distribute. So then in the next step, you're going to distribute. Go ahead and distribute that. So you're going to get 36 over n plus 24i over n squared. Then you're going to get the limit as n goes to infinity of... Now let's go ahead and break this up into 2 separate problems. So let's go like this. This is the sum of 36 over n plus the sum of 24i over n squared. Now this is where it gets kind of interesting, and a review of chapter 1. We're now taking a limit as n approaches infinity, which means we want this to only be in terms of n. Oh, and constants. Of course, constants are always okay. So we want to rewrite all of this using only n's and constants. If I haven't run out of room yet, I'm running very low on real estate here. So let's do this one. This one's the easiest one. There is no I. Yeah. So there are only constants and n. So that's going to be 36 over n times the top number, which is n. We call it the upper bound of the summation. Okay, and then now let's do this one. All right, we got 24i. So what's the formula for I? 24 comes out. The n squared comes out. And then we have the formula for I. using only n's and constants. So that's going to be n plus 1 over 2. And now you have an expression that only uses constants and n's. All right. If there are any more i's in this, then you have not done it correctly, right? Like just like a limit from chapter 1, there can only be one variable, at least in this level of calculus. So now we have the limit as n goes to infinity. I'm just going to copy this all one more time. 36 over n times n plus 24 over n squared times n plus 1 over 2. Which is the limit as n goes to infinity. These n's will cancel. Let's do a bunch of canceling here. So you're just going to get 36. This n will cancel one of these n's. And this 2 will cancel the 24 and give you 12. So you're going to get 12 n plus 1 over n. Hang in there. We're almost there. Don't do the limit till the very end. 36 plus 12n plus 12. Divide each of these by n. Right. So the n in the denominator gets split into two terms here. You get the limit. Well, it's been a while since we did limits, huh? Limit as n goes to infinity of 36 plus 12 over n, which is the limit as n goes to infinity of 48 plus 12 over n. Oh, chapter 1 review. As n goes to infinity, what happens to 48? Nothing. It just stays 48. As n goes to infinity, what happens to 12 divided by infinity? It goes to 0. So as n goes to infinity, 48 is a constant. So it just stays 48. As n goes to infinity, this becomes 12 divided by infinity. Well, you can't put that into your calculator, right? You can't put 12 divided by infinity into your calculator. But you can put 12 divided by a million, right? Or 12 divided by a billion. And you're going to get a 0.0000000 or 0.000000001 or something. You're going to get a very, very, very tiny number, which is approximately 0. And so the answer is exactly 48. This is no longer an approximation. This is the exact answer for this limit. And there you have it. The definite integral by definition. And that's a pretty easy one, yeah? So I really broke it down step by step so that you could see what it would look like. If you're curious what this means, maybe you don't care. Maybe you just want to get the right answer and tell me to shut up. That's fine. I respect that. But I'm going to tell you anyway. I'm not going to do a very good version of it, but I'll say f of x equals 6x is essentially a line. It's a pretty steep line. I'm not going to count. I'm just going to say that's 3. That's 5. This is not to scale. And you have found the exact area, not the approximate, but the exact area under the curve And again, we call it a curve even when it's a line. It's a linear curve, which is also known as a straight line. Although my line's not very straight, but you get the idea. All right. There's so many rectangles, right? There's infinitely many rectangles in there that you don't even have the little, roofs, little steps. There's no more steps. It's been smoothed out, and it's now the exact area under the curve. All right, that's a straight line. You probably know where I'm going to go next. I always go there. A curve. Example 4. Oh, I'm going to set it up as an integral. Calculate or evaluate or determine, or whatever the words we want to use. By definition, the integral, this is the one I was going to do earlier, negative 2 to 4 of 5x squared dx. All right, same idea. All right. Let's try to save a little bit of space this time. Now that we've seen it all laid out, let's just kind of do everything over here. This will be our little bookkeeping area here. Delta x is 4 minus negative 2 over n, which is 6 over n. I don't have to show you to be careful. Negative is a positive, so that's 4 plus 2, 6 over n. Xi is a, so negative 2 plus I times delta x. So that's going to be 6I over n. Right? It's a very similar pattern as last time. F of xi, I might need a little more room for this, is going to be 5 times negative 2 plus 6i over n squared. And again, you could just leave it like this for now, but at some point in the process, you're going to have to simplify it out. So I'll leave it to you to decide if you want to do that now or if you just want to wait till later. All right, that's enough to get us going. So we're going to say the limit as n goes to infinity of the sum from I equals 1 to n of f of xi, which is 5 times negative 2 plus 6i over n squared times delta x times 6 over n. Oh, sorry, they got off the screen. There you go. All right. Now, anything that does not have an I in it can be brought out like a constant. So the 5 and the 6 and the n do not involve I, so they can be brought out to the front. If they do not involve the index I, then they can be brought out to the front. They can only go outside of the summation. So 5 times 6 is 30 over n. All right. Now, the rest of this stuff has to stay inside. So I got negative 2 plus 6i over n squared. Now, you might go, well, the negative 2 doesn't involve an I. Well, it doesn't yet, but when I FOIL it out or when I distribute it all out, it will, or at least part of it will. So I have to wait to pull that part out. I can't pull it out yet. So I've got 30 over n times the sum. And here's what I meant earlier. I waited to multiply this thing out, but now I have to do it. So it's going to be 4 minus 24i over n plus 36i squared over n squared. This is what I would have got if I would have done this multiplying sooner. Although without the 5, because I've removed the 5. So it's like I'm ignoring that 5 and just doing the product, -2 plus 6i over n squared. I skipped a step because of limited space here, but it's -2 times 6, which is -12, and then another -2 times 6, which is another -12, and that's how I got -24i over n. All right, now we're ready to roll. So now we have the limit as n goes to infinity of 30 over n times, ready? 4 times n, right? That's a constant times the upper bound of the summation. Okay, the next one, 24 over n times the summation of I, which is n plus 1 over 2. I'm going to have to squeeze this a little closer together here. We're running out of space. Just a quick rewrite here. 24 over n times n plus 1 over 2. And then plus, I don't know if that helped, 36 over n squared. That didn't really help. And then the sum of I squared. Oh, God, I don't have room for it. N plus 1. 2n plus 1 over 6. Arg. So I'm going to have to steal some of this over here. I'm just going to write that one more time. 30 over n times 4n minus 24 over n times n plus 1 over 2 plus 36 over n squared times, and I'm just rewriting this, n plus 1, 2n plus 1 over 6. Whew, we're really doing math now. You're in the big leagues now. This ain't no T-ball, all right? This is the real deal. The ball is moving fast, and when it hits you, it hurts. All right, here we go. The limit as n goes to infinity of 30 over n. Let's clean up some of this stuff. Oh, yeah. Let's go ahead and put the 30 over n in. Actually, no, let's do some cleanup work first. The 2 cancels with the 24, makes 12. The n cancels with the n. The 6 goes into 36 6 times. This n cancels with one of the n's, making the n squared just n. So we got a lot. It got a lot cleaner already. So I've got 4n minus 12 times n plus 1 plus 6 n plus 1, 2n plus 1 6, n plus 1, 2n plus 1, and then the bottom is still n. Just the bottom of the last term here. Alrighty. And so now we got the limit as n goes to infinity. Yeah, might as well. Let's just go ahead and distribute this. So that's going to be 120 n over n. And so those n's are going to cancel. Minus 360 n plus 1 over n. Be careful, don't cancel them yet. Plus 180 n plus 1, 2n plus 1 over n squared. So that's the limit as n goes to infinity of 120 minus, now be really careful here. You're distributing a minus and a 360. So that's going to be minus 360 n over n minus 360 over n. And then these n's will cancel, but this one will not. Oh, and this one sucks. So let's see. What's the best way to do this one? Let's just hold off on the 180. Just wait on that. And let's do the double parentheses, which I kind of wish I would have done a while ago. But I was waiting, and now I got to suffer. So we get 2n squared. I need a lot of room here. 2n squared, right? And then 2n and then another n, so that's 3n, and then 1 times 1 is 1. That wasn't so bad. Over n squared. So let's see, 120 minus 360 minus, I could just combine those. Let's do that. What's 120 minus 360? That's negative 240? Yeah, negative 240. That's weird. I sure hope I didn't make a mistake. Yeah, it's that darn negative 2 in there. Maybe I shouldn't let it worry me. All right, minus 360 plus, oh, I think we'll be okay. We'll be okay. 180, this is gonna resolve it right here. 180 times 2 is positive 360. There it is. N squared over n squared. 180 times 3. Oh, God, is that 480? Or 560? I'm tired. I'm just going to do it. 180 times 3. 540. My brain hurts. N over n squared. And then the last one, 180 over n squared. Whew. Oh, let's do some canceling. So this n squared cancels with this n squared. This n cancels one of those guys. Hey, you signed up for it. All right, this is calculus. Negative 240, positive 360. So that pause of worry, that worried dad look on my face. I was worried that we were lost. We're okay. Positive 360, negative 240 is 120. All right. We shouldn't get a negative answer, right? Because this is a parabola. It's above the x-axis. I'll get into what negative answers will mean later, if there is a later. I don't know how much longer we can hold out here, but negative 360 over n. Oh, let's combine those too. I got negative 360 over n and positive 540 over n. And again, my brain hurts, so 540 minus 360. If your brain hurts too, that means it's working. If it hurts, it must be the right thing. And then 180 over n squared. Yay! Woo! This means you're almost there. This means you're ready to actually calculate the result, right? So you got the limit as n goes to infinity of 120 minus 180 over n plus 180 over n squared. And the answer, when you calculate the limit of a constant, it's just a constant. When you calculate the limit of 180 divided by infinity, that's going to be 0. Right? 180, it's divided by a billion is still 0. And then if you divide 180 divided by a billion squared, you're still going to get 0. And we did all that work to get the final answer of 120. Man. So each day in this course now, we're nearing the end of our time together. We are like in the last final steps of the peak of this mountain called calculus, right? And so the air is thinner, your legs are tired, your brain hurts, but just hang in there. And when we get to the top together, we'll celebrate and we'll look out at the view and all we've accomplished, and you will be rewarded. So don't give up on me yet. All right. Well, okay. So next example, number 5. So another definite integral. So let's find the integral from 0 to 4. A classic polynomial quadratic function. Ax squared bx c respect to x. So find the definite integral by definition. Here, how about I just say find by definition? That will suffice. Using right endpoints, which is pretty much all we're doing from now on, is right-handed endpoints. All right, so we've already seen the techniques necessary to do this, and this one in particular will, even though it's a larger, expression, because the lower limit of integration, the a, is 0, you'll see that the calculation's a little bit cleaner. And so let's go ahead and find our ingredients. So we start with our delta x. That'll be b minus a over n. It should just be 4 over n. We're doing right-hand endpoints, so our xi will be a, 0, plus I times delta x. Remember, you take the delta x and put it into your xi, which is really just 4I over n. Because that's what makes starting your integral with a lower limit of 0 makes it a lot easier to calculate that. Now, the trade-off for that being simple is the expression, the function, this is our f of x, will be a little bit more extensive. So we've got 3xi, so we put our xi in there, squared, minus 2xi, we put our xi in there, plus 1. So that'll be, now let's just clean this all up at once. That'll be 4I squared times 3. Yeah. So that's 16 times 3, which is 48. 48. And then I squared. Oh, and you're squaring the denominator as well. So n squared. And then this one will be 8I over n and then plus 1. So this is our f of xi, and then this is our delta xi, delta x. All right, so we're going to do this by definition. So the definition is the limit as n goes to infinity of the sum from I equals 1 to n of f of xi delta x. And again, I mentioned this before. Sometimes they'll put a star on the xi. I don't typically do that when I'm calculating, but again, the star just means that it could be any point. You don't necessarily have to use the right-hand point. I suggest using the right-hand point, but it turns out if you use a different point, the result will be the same. All right. I think if you've done a couple of these in your homework, you will agree with me that the right-hand point is the easier one. All right, I'll leave this here for a minute and then it's going to have to go. So we'll go the limit as n goes to infinity of the sum from I equals 1 to n. We start with our f. So this is our f. 48I squared over n squared minus 8I over n plus 1. Times delta x, which is 4 over n. All right, so there's your delta x, and there's your f of xi. Okay, not too bad. So now we got the limit as n goes to infinity. Now we got to decide how we want to break this up. There are a couple different methods. One method is to take the 4 over n all the way outside of the sum. That's one method. Or you could distribute it into each of the terms of the summed, that's what this is called, and keep it inside the sigma. Either way, you'll get the same result. I think I've done it the other way before, so maybe I'll show you this way. You can distribute this in, multiply the delta in. One advantage to doing this is that you have all of your n's all in one, area. You don't have to worry about separating them out like that. You are allowed to separate them out, but it's sometimes nicer to keep them together. So distribute that in there, and all it's going to do is change the denominators. Oh, shoot. And you're multiplying by 4. I spaced off for a second there. So that's going to be 32, and then 4 times 48. Should have that memorized, but I don't. 192. And then plus, and then this becomes 4 over n. So that's one option. The other option is to keep them separate and then, evaluate them separately. I'm going to need more space, so I don't need all these ingredients anymore. Just going to give myself a little more room to work. The limit as n goes to infinity of the sum from I equals 1 to n. So this is going to be 192i squared over n cubed minus the sum from I equals 1 to n of 32i over n squared plus the sum from I equals 1 to n of 4 over n. And now we've got those recipes. Don't take the limit quite yet, so just copy down the word, the symbol for limit, and then now let's do these one at a time. Each one of these will have their own recipe, or their own technique, their own trick, whatever you want to call it. All right, so it's going to be 192. Then there's a recipe for I squared, remember? I is the index, so use the recipe for I squared. That's going to be the n plus 1, 2n plus 1 over 6. Yeah. And then because you have this n cubed here, it's going to be 6n cubed. Minus, and now do the same thing with this one. 32 comes out, and then the recipe for I. Remember, the recipe is based on the index. Just cleaning this up a little bit. It's based on the index, the starting point, starting at 1, and then the ending point, ending at n, or the ending value. So if this one's relatively easy, n plus 1 over 2. And then don't forget you've got an n squared, so just put that in the bottom with the 2. And then finally, the easiest one of all is the constant. So this is like adding 4 plus 4 plus 4 plus 4 plus 4 n times, starting at 1. So that would be 4n. And then it's divided by n, so 4n over n. And there you go. You're done. All of this has a name, actually. This is called Rn. Yeah, Rn is the right-hand sum as a function of n. Or maybe I'll say in terms of. That's a better way to say it. So Rn is the right-hand sum. Yeah, so I've already completed the summation in terms of n. What's nice about that is then when you go to your next step, this is the limit as n goes to infinity of Rn. Yeah. So Rn is just a shorthand for all of this. All right. So we got the limit as n goes to infinity. Let's clean this up a little bit. So we've got n and then n cubed. So that'll change that to n squared. And then we've got 192 divided by 6, which will make that a 32. The more cleanup you do now, the easier it's going to be when you actually get to the last step of calculating the limit. You've got 32 divided by 2 will make that a 16. and then the n will cancel with the squared, leaving a denominator of just n. And then this one's pretty straightforward, just cancel the n's. So now you're going to take the limit of 32 n plus 1, 2n plus 1 over n squared minus 16 n plus 1 over n, and then plus 4. If you do this nicely and cleanly, you won't even need a calculator. Right? You'll just get a nice number here. It should just sort of land in your lap. So you get the limit as n goes to infinity. Let's go ahead and distribute all of this out. That's going to be 32. Oh, we've seen this one before. N times 2n is 2n squared. Then you've got 1 times 2n is 2n. And then 1 times n is n. So that's going to be 3n. And then 1 times 1 is 1. And then don't forget this negative goes with the 16 when you distribute. So that's going to be negative 16n. And then negative 16. And that's over n. And then plus 4. We're almost there. Now we're going to distribute the 32, and then we're also going to distribute the denominator. So this n squared will get distributed to all 3 terms, and then this n will get distributed to those 2 terms. So we're going to get 64 n squared over n squared plus 96n over n squared plus 32 over n squared minus 16n over n minus 16 over n plus 4. Now let's do some canceling. N squared, n, n. Anybody else? How about here? N and n squared. So we've got the limit as n approaches infinity of 64 plus 96 over n plus 32 over n squared minus 16 minus 16 over n plus 4. And here's my favorite part, the limit. Yeah, chapter 1, right? So the whole reason why we learned the limit is so that when we got to this day, this should be the easy part. So you distribute the limit to each of the terms. You could actually simplify some more before you distribute, but I'm not going to do that because a lot of these terms are just going to cancel anyway. So, a quick review of chapter 1. The limit of a constant is a constant. You just get 64. The limit of a constant, the limit as n approaches infinity of a constant divided by n. That's going to be 0. The limit as n approaches infinity of a constant divided by n squared. That's also 0. I don't need to remind you of this, but maybe I do. N and n squared as n goes to infinity are going to get really, really huge. They're going to get into the millions and billions and trillions. And so when you divide, 96 divided by a billion, that's going to be very, very close to 0. It never actually equals 0, but it gets so close to 0 that as n approaches infinity, we consider it equal to 0. We say the limit is 0. We have another constant, negative 16, so that's going to stay constant. We've got another n in the denominator, so that's going to go to 0. And then we've got another constant. And there you go. That'll give you your final answer. So we got 64 minus 16 plus 4. So our final answer, 64 minus 16 plus 4, if I've done my math right, is 42. If you want to just be safe, you can use a calculator. 64 minus 16 plus 4. Oh, I'm glad I used my calculator. 52. I did it on paper and I still got it wrong, so good thing to have a calculator around. 64 minus 16 is 48, and then plus 4 is 52. Every once in a while, you need some insurance. All right, well, that is probably the most complicated. In fact, it is the most intense definite integral that we've done so far. It would have been worse had the lower limit of the integral not been 0. So I kind of, I giveth and I taketh away at the same time, What does this mean? Just a reminder, this is the exact area under the curve f of x equals 3x squared minus 2x plus 1 between x equals 0 and x equals 4. And I drew a pretty good graph. It's not to scale. The y values are not to scale, but this is what the 52 represents. Represents the shaded area between 0 and 4. This isn't a stretched out graph of this function. It's definitely not to scale because these two, the area intersects with the curve here at x equals 4 and y equals 41. I sometimes call this the chimney, or the slanted roof. So again, the diagram's not to scale, but it does give you an idea of what you just calculated. So the 52 is the exact area. Which brings me to the final couple examples of this section. Just a question, does the integral always give you the area? So we'll make a note. The integral from a to b of f of x dx represents what's called the net area between the curve y equals f of x and the x-axis. So the net area, we're going to talk a little bit about what net area is now. So one way to do an example that illustrates the difference between area and net area is to think about it like money, right? So if you had some area that was above the x-axis, we'll call this A1, and then some area that's below the x-axis, we'll call that A2, and then this is A and this is B. Then the integral from a to b of f of x is the difference between a1 and a2. And so the reason is because when you calculate, let's call this point here C. When you calculate the integral from a to c of f of x, that will give you a1. And this will be a positive number. However, when you calculate the A2 would be the integral from C to B. Where am I going to write this? If you did the integral from C to B of f of x dx, you would get negative a2. Because the y values are negative, so the actual area, a2, is the absolute value of negative a2, which would then be positive. So actual area is always positive. Let me give you an example with some actual numbers here. So let's do example 6. And let's just start with a graph that we already have. So consider the graph of y equals f of x. We'll start at 0 just to make it simple. And we'll go from 0 to 8. All right, and we'll call this A1, A2, A3, and A4. All right. So the actual areas of each region are A1 is 9, A2 is 5, A3 is 3, and A4 is 2. Those are the actual areas. Actual area is always positive. Sometimes we call it gross area or total area. Those mean the same thing. I like to use the word actual because the actual area would be if you thought of these spaces as you know, being covered in carpet or tile or you know, some kind of physical substance. I mean, even paint. So if you fill these up with actual substance, even if they're below the axis, the actual space that it takes up is still positive, even though the y values are negative. Let's put some more values on here. Let's call this 3. Let's call that 5. And let's call that 7. And then we already called this one 8. Right. So those are the x values. So what's the total area? The total area is just the sum of all of these. It's the sum from I equals 1 to 4 of AI, which is 9 plus 5 plus 3 plus 2. What's that? 14, 15, 16, 17, 18, 19. So that's the actual area. All right. However, by using definite integrals, we get, well, let's see what we get. Let's do them right up here. Let's do the integral from 0 to 3 of f of x. Well, because it's above the x-axis, you're going to get 9. You're going to get that area from 0 to 3. But if you do the integral from 3 to 5, A2, well, the actual area is 5, so the integral would be negative 5. Because A2, I don't know if you can see that, but A2 is below the x-axis, and so it will give you a negative result. Now let's do this one. The integral from 5 to 7 of f of x dx. Well, that's above the x-axis. That's A3. So that'll just be 3. And then this last one, what did I say it was? 2. The integral from 7 to 8 of f of x dx. Well, I said the actual area was 2, so the net area is negative 2. Now, the total area is 19. The net area would be the integral from 0 to 8 of f of x dx, which would be 9 minus 5 plus 3 minus 2. So what's that? 4, that's 5. Right? 9 minus 5 is 4. 4 plus 3 is 7. 7 minus 2 is 5. You know how I think about it when I think of gross and net? And I mean, this might be helpful for you as well. I think of it like a paycheck. Yeah. You have your gross amount of your paycheck, right? And then you have your net amount, right? So for this example, the gross amount was 19, also known as the total or the actual. And then the net is how much you actually get to keep. So think of the positives as the money you made. The negatives you can think of as taxes or deductions or withholdings, or, you can also think of this as like debits and credits. You in your bank account, you have a debit, a positive number is like deposited into, a credit. A credit is deposited into your account, and then a debit is deducted from your account, and then another credit, and then another debit, and then altogether you have your net amount. So that's one that's kind of already done for you. In the next video, we'll see some examples like this where you have to actually find the area. Let's end this with, we're going to end on number 7 today. Several of these examples today, if you're watching the video and working on the homework, several of these examples today, I ask multiple homework problems, like maybe 2 or even 3 homework problems, all sort of based on the same example. So that's why a lot of these examples are very deep. So this is another one of those where I'm going to kind of get a lot out of this one example. So let's evaluate the following integrals. Let's do the integral from 0 to 6 of 3 minus x dx. And let's do the integral from zero to 4 of 3 minus x dx. And interpret as net area. In other words, think of the answer, or create the answer or deduce the answer, thinking of it in terms of area. So what would this be? Sorry, I didn't have this one pre-prepared for you. I should buy another one of these boards. All right, so you have a function like this. It's not a terribly complicated function. 1, 2, 3, 1, 2, 3, -3. So here is the function 3 minus x. 1, 2, 3, 4, 5, 6. All right. So if you think of this in terms of area, you have the function 3 minus x. So f of x is 3 minus x, which, by the way, could also be written as negative x plus 3. Sometimes that, depending on your algebra experience, writing it as, y equals negative x plus 3, you go, oh yeah, totally. I see the line now, right? It's just a line like this. So there's your graph. Okay. So when we calculate this in terms of area, all we're asking for this one, what is the area here? We'll call that A1. Right? And then the area here. I regret my choices of colors. Oh, and I'm supposed to stop at 6, so the area here. A2. I regret my choice of color because I put the red as being above and the blue as being below. And traditionally you think of red as being negative and blue as being positive, but whatever, it doesn't matter. All right, so think of this in terms of area. All right. And you might notice that these areas are the same. Right? In fact, you could easily calculate them. Since these are triangles, we can use basic geometry. A1 is 1/2 the base times the height. 1/2 base times height. Basic geometry. So the base is 3. Yeah, we're going from 0 to 3. And the height is also 3. So again, we're going from 0 to 3. So 1/2, 3 times 3. I probably should use a dot for times. So 9/2. Or you could say 4.5. Either one's fine. So that would be A1. Yeah. Well, notice A2, the base goes from 3 to 6. So it's also three. Yeah. The base from 3 to 6 is also 3. And the height, is also 3. In terms of area. All right. Now, in terms of net area, it would be -3 because the height is negative. So actual area is also 9/2, which is 4.5. All right. So the net area is negative. For A2. So therefore, interpreting this integral as net areas, the integral from 0 to 6 is A1 minus A2, or you could say A1 plus negative A2. It means the same thing. So it's going to be 4.5 plus negative 4.5. Yeah, or you could write 4.5 minus 4.5. Tomato, tomato, those mean the same thing. Either way, the net area is 0. You can think of these as just canceling each other out. Okay. Now, keep in mind, the gross or the total or the actual area between the curve f of x and the x-axis is equal to A1 plus A2, which would be 4.5 plus 4.5, which would be 9. So you really have to interpret it very carefully. If I say, what's the actual area of the shaded region? Well, the answer would be 9. But if I say, what's the net area? The net area in this example is 0. Because it's like you made money and then you spent exactly the same amount of money, and those two things canceled each other out. All right. So I kind of turning this one problem into 2 examples here. How about this one? From 0 to 4. Well, just take your diagram and chop it off right here. So now you're going to stop at x equals 4. Well, now that we've done all the math, the only thing we do is we have to figure out a new A2. That's a new A2. So the new A2, or the smaller A2, the base is only 1. Yeah, the base is 1 for this small triangle. And the height is also 1. So that's just going to be 1 times 1. Be careful. I have seen even calculus students go 1 times 1 and then make it 2. It's still just 1. I know. You would never do that, especially if you use this. But I don't know. Your brain gets tired. You go 1, 1, 2, 2, and whatever. So this is all just 1s divided by 2, so it's a half. So the area of that little triangle is a half. A1 is still the same. I mean, unless I start at a different spot, A1 is still the same. Okay, so that means that this integral is 4.5 minus 0.5. So the net area in this diagram is 4, because you can think of it as 4.5 is positive and then 4 is negative. And then I could just make one more comment. The total area for this part here between, you know what a quick way to say between is? You've seen this before. On or over, and you say 0 to 4 is 5. Oh, that's interesting. I didn't even plan that, but 5 is the total area of this diagram, which makes sense, right? The red is 4.5. The blue is a half. If you're thinking of them as total or gross, actual, between 0 and 4, it would be 4.5 plus a half, which would give you a total area of 5. All right, we can't, with the tools that we have so far, the calculations are pretty cumbersome. You could have done this using the limit definition, like I did in the last one. However, because this was a triangle, or the graph looked like, triangular pieces, I was able to do it using classical geometry. It would probably take another 20 minutes or so to do this integral the long way. I've already done several of those exhausting problems. In my next video, we will learn the fundamental theorem of calculus, which will wrap up this entire chapter. And then perhaps I will follow that up with some business applications. And that would pretty much bring us to very close to the end of this course. So you've made it, all right? Fundamental theorem of calculus coming next. But until then, I'm Dr. Jordan, and I'll see you on the internet.